thank you. First of all, I want to thank the organizers for organizing this conference and giving me the opportunity to speak about Schrödinger operators with oblique transmission conditions in R2, which is based on the joint work with Jussi Berndt and Markus Holzmann. The talk will be structured as follows. First, we define the geometrical setting and briefly discuss Schrödinger operators with singular interactions. This will some kind of serve as a more motivation for the second part, where we introduce oblique transmission and show that the corresponding Schrödinger operators have somewhat unexpected spectral properties. In the last part of my talk, we will see that these Schrödinger operators arise naturally as non-relativistic limits of Dirac operators. Okay. So before we go into the details, let's set the stage and define a mathematical setting, which we will be assuming throughout this whole talk. Sigma is assumed to be a closed C infinity curve, and omega plus is a bounded and simply connected domain in R2, whose boundary is in fact this curve sigma. Omega minus is defined as the open complement of this omega plus, so to speak, the exterior here of this problem, and nu is the unit and normal vector field, which is oriented in such a way that it points out of omega plus. To motivate the usage of delta potential, we consider in the first step a Schrödinger operator with a regular potential V, and I think it is easy to see that this operator is self-adjoint on this domain H2 if this potential V is real valued and bounded. And as one is usually interested in the spectral properties, it is the next task, so to speak, to characterize, if this is possible, the spectrum of this operator. To answer this question kind of qualitatively, we assume that this potential V is supported only in a small neighborhood of this curve. In particular, it is a zero away from this curve C sigma, and it has large values near this curve sigma. Okay, to proceed, we replace this regular potential by a delta potential of strength alpha, which is supported on this curve. Although the considerations can be done for non-constant interaction strength as well, we stick to two constant ones in this talk to simplify the presentation. Okay, so if we carry out this replacement, we formally change the Schrödinger operator here, HV, to the one on the right-hand side. So at this stage, this is just a formal replacement. But since the potential V is supported in the vicinity of this curve, so it has kind of a profile like this, we expect that the idealized model here involving this delta potential is actually a good approximation in some sense of the one with the regular potential. Okay. Okay, and this in particular, we in particular expect that the spectral properties of this operator here, which are usually easier to deduce, are not far off the ones. What this means is at this stage just formal of the ones we are actually interested in, and this is basically the main motivation in this replacement here. Okay, okay, this is what I just said. Sorry about the first thing. Okay, but we pay kind of a price. We are aiming for a realization in L2, and since this set sigma is of measure 0, restrictions to functions are not really making sense. So the question arises: how can we define this, this corresponding Schrödinger operator? And for this, there are two possible approaches. The first one is to define the operators via the first representation theorem for semi-bounded forms. And in the case of a delta interaction, one defines this one. Considerations of this kind were, for instance, carried out in a paper by Parshin, Exler, Kuberin, and Scheber, or in one of Pankrashkin and Popov. The second equivalent possibility is to use abstract extension theoretic tools, and this is done for instance in a paper by Bernd Lange and Lodoreichik, or in one of Mantile, Posilicano, and Sini, by employing boundary triples and related techniques. And in this approach, one implements the effect of this delta interaction in the form of these two transmission conditions on the curve sigma. Okay, and it's maybe noteworthy to remark that this approach does not need the semi-boundedness, which is the reason why we will be considering transmission conditions in this talk to introduce a new type of singular interaction. Okay, so beside these delta interactions, one can impose other transmission conditions, and for instance, a delta prime interaction is characterized by these two. I didn't say it before, but this delta n is just the normal derivative of the function on this curve sigma. Okay, so these self-adjoint realizations, which implement these two transmission conditions here, are well understood, and it can be shown that in both cases the essential spectrum is given by the positive half-line, and the discrete spectrum, which is then a subset of the negative half-line, is at most finite for a negative alpha, while it's empty for non-negative alpha. Okay. So now the question kind of arises: what about other transmission conditions which are different from the two here above? And this kind of brings us to the ones we are considering in this talk. So in the following, we will be considering these two transmission conditions here, where this delta set is the Wirtinger derivative, which is defined like this. And at first, this definition here seems quite arbitrary, but it will become more apparent when we will be discussing the non-relativistic limit in this last part of the talk. Okay, by using the normal and tangential vector field on this curve, we can rewrite these transmission conditions here in this way here, where there is a tangential derivative term beside the normal derivative one. And due to the appearance of this tangential derivative, we call these transmission conditions oblique here. Okay, maybe I have to stress that because of the formal analogy to delta prime interactions for them, only this tangential term is missing. The question kind of arises if the corresponding Schrödinger operators which implement these transmission conditions have similar spectral properties as Schrödinger operators with delta prime interactions or with delta interaction. And for this, we first have to define an operator in L2 for each interaction strength alpha. And this is kind of and this is done by defining this domain here, which is basically chosen in such a way that all the involved operations here in this transmission conditions are indeed well defined. An interesting observation is that in the case of alpha equal to 0, we have that this operator T0 is in fact the Laplacian defined on H2. I think it's clear that the Laplacian is contained in this operator, so we are left to prove this claim with a converse inclusion. And for this, observe that the domain of this T0 is a subset of the Sobolev space H1. As the transmission condition here on the right-hand side is now S0, implies that the traces coincide. So we have H1 regularity on the whole space. Okay, and then the function which is formed by the two Wirtinger derivatives of this F plus and F minus, which are just the restrictions of this F to the interior and the exterior. This function is in fact the Wirtinger derivative of the function F itself. So if we apply the second Wirtinger derivative, which is basically this term here with a factor 1 with a factor 1/2 here, we see that the distributional Laplace is actually in L2, and hence elliptic regularity implies that it's actually an H2 function. So yeah, this proves this claim. And maybe as a side remark, with the same line of reasoning we did here in this step, one can show that for every real alpha, we have that the operator T alpha is in fact well defined, since then these two Laplacians are in L2. Okay. Okay, so after having defined Schrödinger operators with oblique transmission conditions, we now turn to the properties, and in particular the spectral properties. Okay, and we have this. Yeah, what's the question? Sorry. Yeah, this will be said here. First, for the operator T alpha is self-adjoint for each a real interaction strength alpha, and the essential spectrum is given by the positive half line. Furthermore, if this alpha is non-negative, then one can show that the operator T alpha itself is non-negative, and hence in combination with the form of the essential spectrum, we can add it. This implies that in this case the discrete spectrum is in fact empty. Okay, at this point, it's maybe noteworthy to remark that the first two properties are shared by Schrödinger operators with delta and delta prime interactions. And recalling that these operators have finite discrete spectra, the third item now shows kind of a significant difference to Schrödinger operators with oblique transmission conditions. We have that for every negative interaction strength alpha, the discrete spectrum is in fact countable, and the only accumulation point is -infinity. Okay, so it's unbounded. Furthermore, we can provide this asymptotic expansion for the discrete eigenvalues lambda n's if the interaction strength becomes small. So this is. Sorry. What was the question? This is what we are currently investigating. So this is an open problem right now. So in the case of a sphere, one can explicitly compute this, and by diagonalizing the single layer boundary integral operator, and then one can compute the eigenfunctions from there. So if this kind of answers your question. Okay, apart from these spectral properties here, we have a Krein type resolvent formula where this psi is a linear and bounded integral operator, and this S is the single layer boundary integral operator of the Laplacian we kind of saw in the first talk. And one uses, in fact, this resolvent representation to prove the claimed form of the essential spectrum here. And this is done by showing this that the adjoint of psi is actually a compact operator, and applying Weil theorem on the resolvent difference here. Furthermore, one can show a Biermann-Schwinger principle, which relates the discrete eigenvalues below the essential spectrum with the eigenvalues of the single layer boundary integral operator. And we have in fact that lambda is a discrete eigenvalue if and only if one is an eigenvalue of this operator alpha times lambda times S. Okay, so as the result concerning the unboundedness of the discrete spectrum in the case of negative interaction strength is, I think, the most surprising, I will briefly sketch the arguments of the proof. Okay, so in view of the Biermann-Schwinger principle here, it is sufficient to study for negative alpha the eigenvalues of the compact and self-adjoint operator lambda times S. Okay, so so first one shows that that these eigenvalues seen as functions in lambda converge to zero if lambda goes to zero. Okay, so kind of this behavior here. And this can be done by using known bonds for the operator norm of the single layer boundary integral operator in terms of this lambda here. And then applying a result by Exner and Yoshitomi concerning Schrödinger operators with delta interaction, we can deduce the asymptotic behavior of these intersection points here if we send beta to minus infinity. So if we decrease this beta here, these ENs will move to the left, and the result by Exner and Yoshitomi provides a rate for this. And with this one can now show that the functions lambda times mu S are in fact bounded if lambda goes to minus infinity. So we have this behavior right here. So by proving that these functions are in fact continuous and strictly monotonically increasing, we can apply the intermediate value theorem and find unique intersection points lambda n for each negative alpha here. And finally, by applying the Biermann-Schwinger principle, we have that these lambda n's are the discrete eigenvalues of the operator T alpha here. And since lambda 1 is the first, and then lambda 2 and 3 and so on and so forth, they can't accumulate at zero. So the only possibility for this sequence is to be unbounded. And this basically proves the claim concerning the form of the discrete spectrum. Okay. Okay, so this finishes kind of the discussion of Schrödinger operators with oblique transmission conditions. And in this last part of this talk, I want to kind of illustrate why we consider these operators in the first place by showing that they arise naturally as non-relativistic limits of Dirac operators. And to begin with, we discuss the non-relativistic limit, which will provide a connection between the relativistic description of a quantum particle in terms of a Dirac operator and its non-relativistic description in terms of a Schrödinger operator. And basically, we expect that if the limiting velocity c, which is just the speed of light, is very large to the velocity of the particle, then the relativistic theory is well approximated by the non-relativistic theory. So roughly speaking, we are able to recover non-relativistic quantum mechanics if we perform the limit c to infinity. And this establishes a connection between the relativistic theory and the non-relativistic theory, and thereby allows an interpretation of the Dirac operator D in terms of its non-relativistic counterpart H. Okay. For the execution of this non-relativistic limit, note that as the rest energy, which is in the case we are considering c squared over 2, so the mass is equal to 1/2 here. Since this is a purely relativistic object which has no non-relativistic limit, it has to be subtracted before sending c to infinity. And furthermore, since both the Dirac operator and the Schrödinger operator are bounded, it is the correct way to analyze this limiting process in the resolvent sense, because in this case the operator norm provides a notion of convergence, and this kind of is a breach to the dogma we just heard before. Okay, in the next step, we consider a Dirac operator with a certain delta prime. With a certain delta interaction of this form here. Here, the delta distribution, which acts just on the second component of functions in the domain, is again supported on the curve sigma. Operators of this kind were studied extensively recently, for example, in a paper by Arizabalaga, Maas, and Vega in the three-dimensional case, and by Bernd Holzmann, Umires Bonafos, and Pankrashkin in the 2D case. It can be shown that the corresponding Dirac operator is self-adjoint for every real parameter alpha, and there holds this Krein type resolvent formula here. Here phi and c are again linear and bounded integral operators, and this p is just a projection onto the second component of the C2 valued functions we're considering. This D0 is just a free Dirac operator defined on H1 on the whole space. Okay, so yeah, these are the objects in this resolvent representation. Okay, and for this Dirac operator, we can now characterize its non-relativistic counterpart as a Schrödinger operator with oblique transmission conditions. Okay, to be more precise, this result here holds. We have that the convergence of the Dirac operator D alpha converges to the resolvent of the Schrödinger operator T alpha times the projection onto the first component. And furthermore, one can show that the convergence rate here in this operator norm is in fact of of order 1 over C, but this is not important right now. Okay, so also in this case, we can briefly sketch the proof, and this is basically done by using the Krein type resolvent formula from before for this Dirac operator D, and by identifying the limit of each one of these operators separately, one can prove that these convergence here hold if we send C to infinity. If we now recognize the second expression here as the resolvent of the Schrödinger operator with oblique transmission conditions times the projection onto the first component, we basically finished the proof of this. Okay, to get a feeling of this convergence result and kind of an interpretation of these Schrödinger operators with oblique transmission conditions, we will now consider in the simpler one-dimensional case of a Dirac operator which is supported in the point 0 just, okay? So in this case, one can show that the one-dimensional analog of this Dirac operator D is in fact a Dirac operator with a delta prime interaction. Okay, and for this operator, its non-relativistic counterpart is well known. Stenzel and Scheber showed that it is a Schrödinger operator with a delta prime interaction of the same strength, and hence the naming delta prime for this Dirac operator is indeed justified in view of the non-relativistic limit result. Okay, and in this light, the convergence result in this two-dimensional case suggests to view Schrödinger operators with oblique transmission conditions as non-relativistic counterpart of Dirac operators with transmission conditions that generalize the ones of delta prime interactions to the higher dimensional setting. And this is, of course, compatible with the one-dimensional case, okay? Since in the one-dimensional case, there is no tangential derivative, so the oblique transmission conditions of this Schrödinger operator reduce to the ones of a delta prime interaction. So in the one-dimensional case, these two singular interactions coincide, while in the two-dimensional setting there is a difference. Okay, and to the best of my knowledge, this surprising behavior has not yet been observed. And with this, I want to thank you for your attention.